Welcome to tokenization from scratch. Before a language model can predict anything, it has to turn your text into numbers. That very first step is called tokenization, and it quietly shapes almost everything the model can and cannot do. In this episode, we'll build our first tokenizers by hand, in plain Python, and see exactly why the obvious approaches break. Here's the journey. Today we motivate the problem with character and word tokenizers. Then across the next few episodes, we build byte-pair encoding from scratch, one merge at a time. We add byte-level encoding so nothing is ever out of vocabulary, handle special tokens, compare against GPT-2's real tokenizer, and finally package our own library. By the end, you'll have written every line yourself. Strip away the mystery and a tokenizer does just one thing. It's a two-way translator. Encode turns a string into a list of integers the model can do maths on. Decode turns the model's integers back into readable text. That's the entire contract, encode and decode. Everything else is about choosing what those integers should represent. Visually, here's the whole pipeline. Your raw text gets split into chunks we call tokens, and each token is looked up to get an integer ID. The model never sees letters or words, it only ever sees that list of numbers on the right. Get this step wrong and everything downstream suffers. So the real question is, what should a token be? Let's write the simplest possible tokenizer, one token per character. We read the text, take the set of unique characters, and that's our entire vocabulary. We build to lookup tables, string to integer, and its inverse, and encode and decode are one line each. It's beautifully simple, and it always works on any text. So far so good. Run it, and we get a tiny vocabulary, about 65 characters for plain English. Encoding hello gives 5 numbers, and decoding them returns hello exactly. Lossless, simple, universal. But there's a hidden cost, and it shows up the moment you try to train a model on this. The problem is length. One token per character means a sentence becomes a very long list. And since the cost of attention grows with the square of the sequence length, longer sequences are dramatically slower and more expensive to train and run. Worse, the model has to waste effort rediscovering that the spells the over and over. Single characters just don't carry much meaning. So maybe we should go the other way. So let's swap to one token per word. We split on words and punctuation, and build a vocabulary of every unique word. Sequences are now short, a 10-word sentence is about 10 tokens. But notice that get with default and the fallback. We already know some words won't be in our vocabulary, and that single line is where this approach quietly falls apart. And here's the wall. A real corpus has hundreds of thousands of unique words, so the vocabulary explodes, and a giant vocabulary means a giant, memory-hungry embedding table. Worse, language is open-ended. Any word the model didn't see during training, a name, a typo, slang, a function name, collapses to a single unknown token. The model literally can't represent it. Characters gave us no unknowns but huge sequences. Words gave us short sequences but an exploding vocabulary and unknown words. The fix is to stop choosing between characters and words, and instead learn the right middle ground, subword tokens. Common words stay whole, so sequences stay short. Rare words break into reusable pieces, so the vocabulary stays small and nothing is ever truly unknown. A few tens of thousands of tokens that can spell anything. This is what real models use, and the algorithm that finds those pieces is byte pair encoding. Quick recap. A tokenizer is just encode and decode. Character level avoids unknowns but makes sequences far too long. Word level keeps sequences short but explodes the vocabulary and chokes on unknown words. Subword tokenization gives us the best of both. In the next episode, we'll build byte pair encoding from scratch, counting pairs and merging them step by step until whole words emerge from raw characters. See you there.